machine. Correct score, 10 out of 10.
By now you know how to install the correct software that will allow you to program the Atmega 328P chip, and pretty much any chip for that matter. You know all the basic functions of the chips and got a brief overview of the peripherals, which we'll be using on upcoming videos to make some really amazing stuff. Today is that day! Today is the day that you will learn about actually programming a microchip. No matter what chip you use or what language you choose to do is up to you. That's totally up to you. There's many options. All chips differ in size, memory, peripherals, and the number of output pins, so you really have a lot of choice. For now, we're just going to stick with understanding the basic fundamentals of programming a chip, and we're going to do it in the C language, which is the basis of modern programming languages. Basically, other languages they're like wrappings on top of C in order to make things easier for people to think and type, etc. There are also some functionalities that are included that C doesn't, like how C++ introduced object-oriented programming, but we're gonna step away from all that and just focus on what C has to offer for you. Why C language in 2019? Why? Why?
Why? Why? Why? Why? Why? Why?
C is the language that allows you to program in human terms and still be able to talk to the chip at the hardware level. That's what you need to understand. That's the most important thing for you to understand right now. C offers you the ability to still think like a human and type like a human, but be able to communicate with a chip. What do I mean by that? Other languages like the Arduino language are simplified wrappings, usually on top of C or C++ even, that translate code in C into more readable, child-friendly language that makes everyone believe that they can program robots. Well, good luck with that. I've been there, and I truly wish you the best. Bye. Okay, now that those people are gone, it's time to learn the secrets of a C program. In C, we can directly flip the bits inside the chip on or off. Think of them as light switches. For the Atmega 328P chip, it is capable of computing 8 bits of data. 8 bits are like 8 light switches in a row, like you see here in this graphic. These 8 bits are also known as 1 byte. So 8 bits equals 1 byte, so 8 switches, right? Now you can see where the term megabyte comes from. So mega means million. That would be 1 million bytes. Remember, 1 byte is 8 bits. You following me? Great. Giga means billion. That is a lot. Our chip for this series of tutorials only does 1 byte. However, that is still a lot, and it is very fast. It's faster than you need as a beginner. It's really amazing. So don't worry. You don't need a lot of hot, steaming, bit crunching power to move motors, turn on LEDs, etc. You can still make amazing things. So take a deep breath. Our chips are a little over $1 instead of $300. And if you decide to really go with this and hammer our way at it and make a lot of stuff, and you really understand how chips work and you enjoy programming them, yeah, you can move on to those higher, more data crunching chips that are more expensive and need heat sinks because they get so hot inside because they're flipping on and off the switches so fast and so frequently, and there's resistance in the transistors and the wiring, and the heat is dissipating, etc. There's so much going on, right? Yeah, you can get to that point, but just be happy that you don't have to start from there. You can start with the cheap option that's still going to do amazing things. So different combinations of light switches do different things on the chip. All right, enough of that. Let's open up Programmer's Notepad or whatever program you have installed. I'm sorry if you have a Mac. You can look up a substitute to program the AVR in C. Just believe in yourself. Today is that day. You're going to learn how to do a C program, and you're going to do it pretty quickly. So get ready. You're going to learn a lot. First thing you need to do is to understand how files work on your computer. The first thing we'll do is take a look at the files of my computer, so it will help you understand how yours work in your computer. This is based upon like a Windows computer, how a Windows computer works. However, all file systems are very similar, and Windows, Mac, Linux, Unix, they're all along the same path, okay? So just calm down. You're gonna be fine if you have a Mac or a Linux. You're gonna figure this out, and there's people who have been able to program on their machines just like I can on Windows, so don't worry. Let's take a look at the files that are on my computer. You'll notice that my computer is basically broken down into 3 separate drives that I've installed. Most people will just have one, and by default in Windows it's the C drive. In Mac, I don't know what you call it, but I know that there's a default drive and so on, so I'm pretty sure you can figure that out. You can see I have games on my A drive, I have my C drive with most of my Windows stuff, and I have my AVR stuff, and my documents and downloads are also on there by default. Also, I have a separate games and programs drive. So let me show you how a C program works. The first thing we need to do is to go into our AVR folder. I want you to make a folder titled AVR. You can title it anything you want, but let's just title it AVR to make this simple. In AVR, you're going to make a lot of different files. These files are different projects, and each project has a name. So you'll notice that each of these have different names, and these are just names that I've made up. You also notice that I have libraries in here. There's a folder called libraries. This is not my library. This is my collection of libraries that I've taken from the book that I've studied from, or from the internet. This is where I put them. The thing that you want to keep in mind is everything needs to be in the same general path. So all of my AVR files are going to be in the same folder, and I've titled it AVR. So make sure you have that set up like that. The reason for that is when you start having header files and other C files that you're going to include, they all need to be along the same general path, like in the same general folder. You can see libraries is in here. So I can pull different functions that are predefined, pre-labeled, from the same general folder, and then my compiler is going to be able to access those and include them appropriately when I call them in my C program. That doesn't make sense to you right now, but it is going to make a lot of sense later. So just keep that in mind. You can't just make files all over the place. You need to keep them all in one place. And if you put it in a different place, don't worry, you can move it over into this folder if you need to. So if we want to start making a C file, we need to open up something like Programmer's Notepad here. You want to create a new project and just choose C, C++. That helps to select the template of all the formatting and coloring and all the schemes that you want to set up that I showed you in the previous video. You can change the font colors and everything. It's going to be in this. So that's why you want to select C, C++. And this is how you do a C program. Boom, done. Let me explain what all this means. There are 3 different basic parts to a C program. The top part is called the preamble. And in the preamble, we include various header files. And those header files end in .h, as you can see here. Sometimes you'll see like a .c, but generally we don't want to do that. We can reference the C file in the header file itself. The C file can reference these header files, etc. You don't really want to include a C file, although you can. You can also define things up here. So say we want to include some sort of predetermined integer, the amount of time we want something to delay. We just say, what do you call this these days? Hashtag or hash, #, whatever. And we're going to say define. So we're defining a specific variable, and let's call it blink speed or blink delay. Let's call it blink delay. Notice I start with a lowercase and the second word starts with an uppercase. This is just the way that people generally have done it, and if you follow what other people have done and are currently doing, it's going to be easier for you to read their code and to learn from their mistakes and to learn from their code, etc. So I suggest just following that. It makes it a lot easier. You could also just do like an underscore and then like delay like that. It's totally up to you. It doesn't matter. So this can be anything. You can type unicorn ponies, whatever you want, and then you need a space, and let's just select the value of 200. I'm going to show you what that means in a minute. So the preamble contains all of your include files. So you type this # and then include, and then we have the basic input output a header file for the AVR chip that's already been made for you. It's included when you install the tool chain that I showed you how to install. That's all included on your computer already. So it has some stuff down here like how to reference the data direction register B and port B. That's all defined in AVR/IO.h. And make sure you have these carets. Okay, so open caret, close caret. And this is the one for the utility delay header file. This is going to come in handy later on when we choose to delay the chip. And this is, you want to do this when you want to have a delay where you turn it on, you wait a certain time, and then you decide to turn it off later on. So that's the preamble. The second part is called main, and main is just written like this: int space main, and then you have a parenthesis, and you have void, and you have another close parenthesis. Make sure you have a space and an open bracket, and then that open bracket, if you can see, my program's notepad is pointing out. You can change the color that it highlights, but what's really cool about programs like Programs Notepad is they show you where the other bracket, the corresponding bracket is, and that's the one we want. This is where it actually closes. Okay, so main is open, and it has another part to it, which we're going to get to in a second, and then it closes here. So every door that you open, you must close on your way out. Just think of it like a house. You're going into a house, you open the door, you see a bunch of stuff in the different rooms, you turn on some things, turn off some things, and you close each door on the way out. So in main, we have initialization. So you can call it init, like inits. You can see here I labeled it inits. One thing I want to point out to you is you'll see these comments that I have here. If you're going to have one line comment, you don't even need that on the end. That's just for show. If you're going to have one line comment, you need to have 2 slashes like that, 2 forward slashes. So that does one line of comment. If you want to have multiple lines like this, all you have to do is do a forward slash and asterisk, and then you can type whatever you want for how many lines you want. And then you're going to have another asterisk and then another forward slash. Here I have it on one line. It also works on one line, but the main use is for multiple lines of comments. And sometimes you want to write it like this and make it look really nice. The reason you want to have comments in your code is because you may not make a program every day, and you'll come back to it a few months later even, and you're not going to remember what it said. You're not going to remember why you wrote it. You're not going to remember what the problems were. This is where you can write it, and you'll have it for reference later. Or if you want to share the code with people, they'll be able to understand your code. So keep that in mind. This is to turn on the data direction register B. If you remember the diagram, I'm going to show you down here, the diagram that I showed you of the chip. Data direction register B contains all of the port B pins. So what we need to do is set those pins to output. So we're turning these pins on output. This is just a very basic program, so calm down. If you already know how to do this, calm down, okay? We're teaching beginners here. This is gonna make it easy so anybody can get this. Data direction register B, and we're gonna say equals, and this is the 8 bits that I showed you just a second ago. 8 bits, so we have 1, 2, 3, 4, 5, 6, 7, 8. All you need to do is turn on the first bit, which is all the way on the right. That turns all of the pins to output. Okay, I wrote it right here for you. This is what that says. And then we need to close this statement with a semicolon. In C, this is how we close each statement. If you don't do that, it's like not writing a period in a sentence, and the compiler will throw an error. It'll say, hey, you didn't finish this statement out. I don't know when to stop. You need to learn how to do that, okay? Next, we have the event loop. This is called loop. And within main, we have an open bracket. And then once you finish calling all of your actors to the stage and setting them up in line and telling them how they're going to get ready for the show, this is where you write the actual show that's going to be taking place over and over and over and over again, basically until the chip runs out of battery or the end of time. So we start this by typing while, and you notice I space it inside I have about 2 spaces in here. Okay, spacing helps to organize your code, and if you're familiar with other programming languages like Python, you're forced to space appropriately, and that really cleans up the code and makes everything look really nice. And for things like Python, it won't function, it won't compile unless you have it formatted correctly. So I have it indented a little, and then I have while. This is the loop language, while, and then I have a space, and I have in parentheses, I have the number 1. 1 means on, basically. So you see we turn this bit to on. This also is on. So while, basically while the chip is on, while the chip is running, while the program is running, we have another open bracket, and then we have port B. So in the data direction register B, which is all set to output, all the pins in data direction register B are set to output. We're turning port B pin 0 on. Okay, so this is 0 and 1. So if it's set to 0, you know, it's off. If it's set to 1, then that's, we start counting from 0. So PB0, that's PB0. Okay, the first pin, the first LED pin, the first bit is PB0. And you'll see that in the diagram down here. PB0 is this bit right here, the first bit. The second bit would be PB1, PB2, PB3, and so on. This is all it is. There's other ways to do it, like you can have a header file that you include up here, and you can call it whatever you want. You can say, you know, like pin layout.h, and you can include it, and I'll show you how to do that later. So if you wanted to just do it a simpler way, you could have your predefined header file that labels all of these different pins in this diagram on port B, and you can simplify it, and you'll be able to do something like PB0 and then bit shift it with a 1 like that. So you see how much easier that is? I'll show you how to do that later on. It's pretty simple, and you're gonna really like it. So for now, we're just gonna leave it how it is. So this is PB0 turned to on. So they're all set to output with just the 1, that's all we need. Another way that you could write it is like this. This is the hexadecimal format. In hexadecimal, if you look that up, that basically means everything is on. So that's the way I like to do it. It's just shorter, but just for the sake of showing you how things work, I'm gonna show you this. All right, and then we have our delay. This is only possible if we include this header file up here, this delay header file. And it's the way it's laid out. And if you look into this header file, you'll see that it's laid out as underscore delay underscore and then MS. MS stands for milliseconds. And we have a value of 500. Let's say we want to use 200. All we have to do is type in blink delay. So instead of typing in 500 every time, you can, you know, just type in blink delay. And this comes in handy when you want to have your program alter this value as it goes, right? You can increase it as time passes or decrease it as time passes, or if certain events happen, you know, you decrease or increase the time that it's being delayed. You have a lot of options to do that. And that's why you would want to use a label for the value. So you're just referencing the label. So you don't have to always see what it is. You could just, you know, have the label, and then in the program you can have the program alter the value that's attached to that label. That may not make sense to you now, especially if you're new to programming in general, but it will make sense fairly soon. So let's just set it to blink delay, which is 200. And then, so that'll turn it on, that'll turn the LED on, and then it's gonna wait 200 milliseconds. And then we're gonna turn it off. You see that? All we did was turn the PB0 from on to off. Okay, and make sure you have the semicolons after each statement. All right, and then we have another delay. So we turned it on, we waited 200 milliseconds, we turned it off, and then we have a long delay of 1000. You could do something like blink delay plus, you know, whatever, 1000 or whatever you want. Let's just say 1000 just for simplicity right now. And we'll take a look at how that looks. And we have the semicolon to close that out. And then we need to close the doors on our way out. So for the loop, we have this open bracket and we have this closed bracket, and then we have return 0 and a semicolon. This is just good practice in general for C programs. For normal C programs, like, you know, for a computer, you have to have this. It means you're just ending the program. You're not getting anything in return. It just ends that loop. Just write it, just follow it. You don't have to worry about it. Just include it. And then you have the final bracket like I showed you before. So everything looks clean, and we are almost ready to flash the program to our chip. The first thing I need you to do is to go ahead and you notice that there's no name, right? You need to go into File and click Save. So here's a folder that I already have. Let's make a new folder. So I'm in AVR. You need to make sure you're in your AVR folder. Okay, so make sure you're in your AVR folder or whatever folder you title for all of your programs. And let's make a new folder. We're making a new folder called New, and then capital B Blink, and then capital LED. So this is my new Blink LED program. All right, so that's the folder. And then in new Blink LED, we're gonna call it the same name, New, capital B, Blink, and then all caps LED. And we wanna save it as .c. That is all you have to do to save it as a C file. Windows already knows to save it as this file format. It already exists. You don't have to go through here and, you know, don't worry about changing the format. You don't have to do that. All you have to do is just type in .c. and then save it, and then it's ready to go. So let's take a look. So if you go into AVR, so I'm in AVR, you can see my path here. If I go into AVR and I scroll down, let's make sure I refresh. If I scroll down to here, oh, there it is, new Blink LED. And look at that, it's right there. If I double click, it just brings up what's already open, new Blink LED.c. All right, the one thing that you need to include to make sure this works is a MAKEFILE. If you go to my website, you can see the MAKEFILE that I have that was provided to me by Elliot Williams. He's the one who wrote the book that I really, really like. It's made by, it's put out by Make, and it's called AVR Programming, Learning to Write Software for Hardware. So that's Elliot Williams' book. You can find it on Amazon. I highly recommend it. It goes really into detail, and it's really funny, and he has a lot of jokes in there. I don't know if he did it intentionally, but there's a lot of puns. So he makes a very complex, in-depth topic fairly accessible and digestible. So I highly recommend that. It took me a long time because I was new to everything, but for some of you, you may get it faster than I did. So we're gonna go into, let's see, I need to find this MAKEFILE that I have. Pretty sure it's in libraries. Gonna be, here's the MAKEFILE. Okay, so I'm just gonna Control C, and I'm gonna pop that into my new Blink LED folder. Control V, boom, there it is. These are the two files that you need in order to start flashing a program. So let's take a look at that. I'm gonna double click it and choose, not Notepad. Notepad doesn't have any formatting. I wanna use, Word is too much. I like to use WordPad. It's light, but it also keeps the formatting. So here's a MAKEFILE. The MAKEFILE is essential to flash your chip. It basically sets up a lot of different parameters for the compiler to access in order to program your chip successfully. So let's take a look. The first thing is your microcontroller. All you need to do is edit this appropriately. We don't have an Atmega 168, right? We have the Atmega 328P. So if you're using a different chip, if you know what you're doing, make sure to change this. The CPU rate, it is not 16 megahertz. That's like an Arduino. We need to bump that down to 1,000. Or not 1,000, 1 million. Is that enough? Can't see. 1, 2, 3, 4, 5, 6, 1. Okay, so that's the CPU. That's the clock speed. The baud rate, just leave it at the default 9600 up or lower. And like he says, you could try these different ones. That's for serial communications, like when you want to talk to your computer or other peripherals or other chips and etc. You send data through serial communication, and that's what that is. Anyway. So make sure these are set up appropriately. If you have this wrong, your chip might not be programmed successfully. So that's where you could start troubleshooting. Next, you want to come down to the programmer type. I recommend, I was using a USB ASP, it didn't work. Now I use the USB Tiny. And then lastly, all you got to do is scroll down to the target program. So the target program is the name of your file. So right here, you'll see the target. I scrolled down a little bit too much. So if you scroll down to here, you'll see the target. It says blink LED. That's not the one I want. I want the new name, right? Do you remember what it was? New blink LED. And that's it. So notice that he says without the .c. You don't need the .c. All right? So you want to make sure you save this file. You want to save it. And you can copy and paste to new projects, and then you can edit it every time you do it and change. Basically, the only thing I ever change is the target name, the target file, the C file, because that's the only thing I'm changing. Everything else I pretty much keep the same. Unless I'm working with servos or something like that, I might play with the CPU speed, or if I'm doing serial communications, I might change the baud rate. It depends. I haven't really had to mess with anything yet, so don't worry about that. All right, so that's saved. And we have our C file. So now you go back into Programmer's Notepad. In Programmer's Notepad, you're going to look at Tools. And here you're going to see it says WinAVR Make All. So watch this. When I make all, it's going to tell me if there's any errors. 0 errors. Okay, it took 1 second. And some of this data down here, this is just the stuff that we used to have to type in. Not all of it, but some of it you'll notice we had to type this in when we were trying to program a chip. This is like the format we would have to type in the command prompt. But now we can just use AVR dude SS to do it. And if we look at our file, look at that. We have these new files that are generated. The one that we need to flash the chip is the hex file. You don't have to worry about the other ones. These are all part of the process, but the one that you need to flash the chip is the hex file. So go to AVR dude SS. We'll just call it AVR dudes. And once you detect your chip, you want to see, look, they're still up to date. Look at this, October 11, 2019. They keep on top of this. People care about this. We're going to do that later. So you want to go in. You see how this is my old blink LED file? We want to find the new one. And it's in the AVR folder, and it's called new blink LED.hex. Do you see that? It's that same file right here. That's what this is. It's only showing the hex file because it only wants the hex file. That's it. And then make sure your programmer is the appropriate one. Mine's a USB Tiny, the one that I highly recommend because it's no nonsense. I got mine from SparkFun. It was already assembled. Make sure you get it with the cable, the ribbon cable. It's the converter cable that converts from 10 pins down to 6. It makes it a lot simpler. The 10 pin just has a bunch of unnecessary ground pins, and the 6 pin header just, it links those all together and puts it down to 6. The only essential ones that you need. The port needs to be USB if you're using the USB Tiny, and you click detect to detect your chip. You need to make sure your fuses are set appropriately. So just copy the fuse lock bits I have here. That's a topic for another video that you don't need to know now. Basically, this will help set your clock speed on the chip. They come 1/8, factory clocked at 1/8 of the maximum speed. Just follow what I have here, and this will coincide with the MAKEFILE speed that we defined a second ago. If this is not set appropriately, it will not flash to the chip successfully. And here is just what I was talking about a minute ago. This is what you used to have to type into the command prompt. So every time you were trying to flash the chip, you'd have to type this in. Before we flash the chip, I just want to show you a quick tip. if you make a change, say you realize you made a mistake. Say you want to change this to 300. Okay, you save your file, you go into Tools, and you make clean. Make clean is going to erase all those files. See how they just disappeared? Because you need to generate new files to accompany the updates to the program that you just made. And then you just click Make All. I do this a lot, so you really need to know about this. And if we go back to the file, boom, there they are. And you don't need to retype in, you don't need to find the file again. It's the same file. It's still looking at that same direction, but I just do it, just for good practice. Just double click on the new file, although it's the same name. All right, so now let's go. Before we click program, we need to make sure that our breadboard is set up appropriately, that we have the LED correctly connected to PB0, and that we have our power cables and our programming cables connected correctly. So I'm going to show you how to do that first. Let me show you exactly how to do this in the easiest way possible. First, you'll notice we have PB0 right here, just like our diagram. On PB0, right, pin B0, I have my positive lead. How do I know which is the positive? It's the longer one. The longer one that you could cut up and make a cross with it, a plus with it. That's the positive one, the longer end of the LED. So you just stick that into PB0. And then the negative end, we're just going to put it off to the side. It doesn't matter where. You could put it over here if you wanted. It totally doesn't. It really doesn't matter. So just put it off to the side there. Make sure it's equally, it's in there good. All right, so now let me show you my programmer. I showed you my programmer in the previous video. I really like this one. It's a no-nonsense, no-hassle programmer. It's called the USB Tiny AVR Pocket Programmer, and it has the option to power your device. You can power the target. So that means you don't have to have a separate battery supply when you're testing the programs running through this chip. You can just use this, and it's very safe. Even if you get the wiring mixed up, or if you accidentally bridge the ground and the voltage, this chip is safe. The board is very well designed. I really, really, really like this. And this is a ribbon cable that just attaches to it. I think I had to opt for this to be included in the package, but you can see it's normally a 10-pin deal. So there's 10 pins. And this header, this ribbon cable just simplifies that, because if you look on the back, you'll notice there's all these ground. Look at how many ground there are. You don't need all these. And then look at this NC one. You don't use that one. That one's not used. So all of those can be eliminated, and you only need VCC, BOSI, reset, SCK, and MISO. That's how I say it. I don't care. Master out, slave in, and master in, slave out. That's what those stand for. So it just bridges all the grounds together, and the NC it just doesn't use. So that's all this cable does, and it's essential. You can see, look, see how it just cuts it off where you don't need it. This is a great thing to have. You really need to have this. And here you'll see there's a notch. So you see this little notch right here? That's going to be your reference, because this gets really confusing sometimes. The notch is going to show you where you need to put the wires. So I have my wires color-coded for you for simplicity. So on the top left, you're going to need to memorize this or write it down. On the top left, we have voltage, VCC. The blue is going to be our master out, slave in. I call it MOSI. The bottom is going to be our ground. So we have voltage, ground. Okay, I have gray. You know what? Let's swap it out for black, actually. Just makes it easier. Most people use black for ground, so that's what I'm gonna do. All right, so we got our black for ground, and at the top we have our MISO, master in, slave out. We have our SCK, serial clock, which is the green, and then we have our reset. The reset must be connected. There's a there's like a resistor. It gets pulled, and then it puts the chip into a programmable mode. So anyway, that's what that is. I'm not going to explain all of this. Serial clock is just, it sets the clock, you know, so that the chip can communicate successfully with the computer. Anyway, that's all unnecessary information at this point. So let's just hook it up. I'll show you exactly how to hook it up. So we have our LED set up, and we need to put in our reset in the top left. Boom, just like that. And then we need to put in our SCK. So I just count up, this is the easiest way to do it. I just count up 2 from the bottom, and then these 3 are going to get 3 wires. The SCK goes on the topmost of that 3. And then we have meso, which is my yellow. And look, remember, you can do any along this rail, it doesn't matter. I like to spread it out because it's easier to make sure that everything's plugged in. And then Mosey is on the bottom. So that's my blue one. So SCK, meso, Mosey. I call it suck, meso, Mosey. All right, there we go. Now we need to make sure that our voltage is applied. So I have this marked here as red. We're just gonna pop it in right there. Normally you'd put a small, simple capacitor across these just to make sure the voltage is coming in at a steady rate. Don't worry about that right now. We'll do that later. Okay, now I'm just gonna pop that in. All right, now we need to make sure that our LED. Now we need to make sure that our LED has our ground connection. So remember, electricity needs to flow in order for anything to happen. So right now it's going through the chip, but it's not really coming through this LED because it doesn't have anywhere to flow for ground, right? Just think of like voltage is high pressure, ground is low pressure. If you just have high pressure, it's not going to go anywhere. It's just going to like stay there, or the opposite. You know, if you just have low pressure, you need the 2 opposites in order for it to go. So let's just hook up this gray wire to the same rail. Okay, we're on the same rail. Doesn't matter where. And then we're going to pop it right into our ground rail here. All right, it's good to go. If you hook up your chip exactly as I have shown you, it's going to do it. And you could double check it. You can double check it by going into AVR Dudes and clicking detect. AVR Dude error could not find USB tiny device. Why is that? Anybody know? Could anybody tell me why? Because it's not plugged in. All right, so just make sure that's plugged in. Plug it in anywhere on your computer. Okay. So there you go. All right, so now let's detect. Okay, detected at Mega 328p. So make sure everything's good to go one more time. You would be amazed at the smallest things that will prevent you from programming this chip. Make sure your hex file is correct, and then click program. Wow, that was super fast, right? Because this program is very simple, it's very light, it's very quick. So you can see all the different processes it went through, and if you care about that, you can take a look at that. And so what it did was it wrote, and it took 0.43 seconds, and this is what it wrote, and then it read it back just to make sure it wrote it successfully, and that took 0.23 seconds. And then so that's, you know, it verified it. And then it took 176 bytes of the flash memory that's on the chip, and it verified it. So now let's take a look at our chip. All right, so you can see it's blinking like a crazy maniac. Look at that thing go. Look at that. Oops, oops, oops. Think of all the rave parties that you could have with this thing. Look at it go. All right, now let's change it up a little bit, right? Let's change it up. So let's go back. So let's go back into Programmer's Notepad, and let's change the delay. So blink delay, let's just say 1000, and then we'll go down here and say blink delay, just to test out, you know. So we, instead of writing the actual thing, And then delay milliseconds. Let's do that like 200. And save, make clean, make all. There were no errors. I was watching it. And then go to here, program. All right, now look at our chip. Look at the LED. It's a little bit different, right? So it's on for a longer time than it is off. So you can think of all the different things that you can make just with LEDs alone, blinking. Think of all the things in this world that are just LEDs blinking or simple, neon lights blinking. You could make a lot of stuff with just a chip and blinking LEDs. And to get you thinking, you can have different things happening on each of these different pins, as many pins as you need. Not all of them, but most of them. You can use them to make some sort of blinking LED device. You can have a button connected to one. It's totally amazing. We're going to check it out in the next video. So I hope this clears up all the confusion of programming anything in general, especially chips like this. And this is the start of your career in robotics, basically. This is the start of your journey. Let's call it a journey. You don't have to necessarily have a career. This is your journey in robotics and electronics. It starts right here with this blinking LED, and we title this Hello World. This is how you say hello to the world, is with a blinking LED. So congratulations, you made it through to the end of this video. If you liked it, make sure you let me know. If you have any trouble, comment down below, and there's going to be people who are willing to help you and other people who have problems. And from my experience, I had so many problems, everybody. I had so many problems just with the dumbest things, really. Like just getting the semicolons in place, or correctly labeling something. I misspelled something, or I had the wires weren't connected. The other day I couldn't get this thing to work because I had for my website I had showed the back of this breadboard, and something was loose inside, and it wasn't allowing the LED to connect successfully. So it wasn't doing anything. The chip was flashed, and the LED would just sit there, and it would be a dull, on. That's all you have to do. And look at this. You could take these off just to prove, and you could take these off as well. All you need is like a battery source. You could have a battery pack of 3 to 5 volts going into this chip. And like I said, it's good practice to put a capacitor over top of these, like a simple small scale capacitor. But we're going to get into that as you go. That's the thing that I want you to keep in mind with this hobby, is you don't have to know everything from the beginning. That is such a stupid concept. And I'm sick and tired of people trying to tell everything in one video and trying to, just illustrate too much. It's dumb. So congratulations, pat yourself on the back, and get excited for the next one, where I'm going to show you how to make